Physics Notes, Unit 24, Electromagnetic Waves. Basically, just a general overview. We have the issue once again where we have to visualize something that's invisible, and it's three-dimensional, and we have to represent it on a two-dimensional piece of paper. You are sitting in a room that's full of invisible stuff, magnetic fields, gravity. All these things are active. There's all kinds of electromagnetic waves. For example, a good example of electromagnetic waves are radio waves. The room you're sitting in right now is full of radio waves, invisible to your eyes, invisible to any of your human sensors. But if you took a radio in your room right now, turned it on, you could tune into probably 10 or 20 different stations, probably 5 or 10 AM stations, 5 or 10 FM stations. Those radio waves, which are electromagnetic waves, are in that room right now. Now I have a picture here of something that represents an electromagnetic wave, but let me go over the definition once again here. We did talk about these way back, I think in Unit 16, just an introduction. But it's a transverse vibration of mutually inducing perpendicular electric and magnetic fields. There's no material substance, and they don't take a material substance to travel through. They do not need a medium. In fact, they travel best through a vacuum. The speed in a vacuum we call the speed of light, because light is an electromagnetic wave, is 3 times 10 to the 8th meters per second. And some radio waves can go through a lot of electromagnetic waves can go through a lot of things. Like X-rays can go through a lot of things, obviously. Gamma rays, radio waves can go through walls. Light waves are one of the electromagnetic waves that can't go through a whole lot of things. It can go through clear materials like glass and clear plastics, but it can't go through, like walls and wood and opaque things. But kind of by definition, but just by its nature, it can't go through as many things as radio waves or X-rays. So there's different penetrating powers of the different electromagnetic waves, and there's different energy levels, and also kind of another topic that we won't get to, but we're treating, these are, we're talking about waves here. All of these waves also have a dual nature. They have a particle property, and that's referred to as photons. All of these can be treated like photons, but that's for a future course in modern physics. Just wanted to say that right now. But bottom line is, going back to this diagram here, this is a way that we can depict perpendicular fields. So you gotta envision the three-dimensionality to this. Also, the fact that this is in all directions three-dimensionally. But there's a magnetic field here represented by the blue arrows. That's horizontal vibrations. And the electric field, that's vertical vibrations. And they're mutually vibrating. They kind of are self-generating at that particular speed. Now, there's nothing magical about the red being up and down, and red's not even magical. I mean, I'm just showing you that, or it shows you that just to kind of get a better picture of the three-dimensionality here. But the electric field, sometimes we just say the E field, could be horizontal, and the magnetic field would be vertical. Or the electric field could be at a 20-degree angle or a 30-degree angle. So there's nothing, once again, saying that it has to be straight up and down. It could be any angle. And in fact, they are. Light coming out of a light bulb has all different kinds of orientations to the different fields. But any particular wave, the electric field and magnetic field are always perpendicular to each other. And they're perpendicular to the way the wave propagates. In this case, this wave is propagating to the right, according to this arrow right here. It says here's the direction. So the electric field is up and down. Magnetic field is oscillating forward and backwards. And the direction of propagation of the energy is to the right. Alright, so that's a quick overview and a little picture of that. So you got to kind of envision that. If I go down here a little bit. So there are some... Alright, please work here. Alright, got this working. So you've probably heard of this before. The electromagnetic spectrum. In fact, the visible spectrum down here, you've probably heard this before. Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. That's just the first letter of each of the 7 colors, even though there's millions of colors and millions of shades of colors, but we break it down in these basic colors in this particular rainbow. Okay, it's a small sliver of this overall electromagnetic spectrum. This is the sliver, so this is an expanded view of this little sliver, which is even still bigger than it should be in proportion to this overall spectrum. This is the one that's detectable to our eyes. The rest of these, we need radios or other sensors to sense those kinds of waves. In many of these diagrams that you'll see, I like to start with the lower energy on the left, the radio waves on the left, and go up to the higher energy on the right. But if you look at diagrams, half the diagrams will start with the high energy on the right and go to low energy on the, or high energy on the left and go to low energy on the right. So they'll just flip the whole thing. But they're always in this order. Like I always start with radio waves, lowest energy, big wavelengths. So these numbers right here represent wavelengths. Sometimes they'll have the frequencies there. These would be low frequency. And we're going to calculate some frequencies in here in a little bit. And we've done some of that already. But these are wavelengths, 10 to the 6th power. That's like a million meters in wavelength. So radio waves. And there's all kinds of rules governing what radio stations can use what radio waves, what frequencies. And there's international agreements over using different frequencies, whether it's for Bluetooth or for your radios or for your doorbell even, or walkie-talkies or GPS, handheld GPS. There's all kinds of rules to govern the use of this so that people aren't interfering with other people's signals. Also some security issues that are involved with that. Microwaves in this from about 10 to the 0, which is 1 meter. 10 to the 0 is 1. 10 to the negative third is a millimeter in size. Microwaves in that range then. I mean, TV is also in that same category as radio, by the way. It's left off of here. Infrared, that's frequencies that are just below visible. Infrared radiation is easily absorbed by things that are warm, it's an emission from things that are warm. Things that are warm, like especially like a human body or anything that's warm, basically, can easily give off infrared rays based on the vibrations of the atoms and the molecules in that particular object. But infrared, and that's a lot of times those are used in like remote controls for like TVs and garage door openers and things like that. Then you have your visible spectrum from lowest energy, which would be the biggest wavelengths. So these down here represent wavelengths. Red is in the range, there's like a range from 750 to 700 nanometers-ish for red. Yellow is about 600 nanometers. Those are the wavelengths. Then ultraviolet, that's the kind of rays that have more energy, and they are the ones that are more harmful to like your skin and so forth. It can cause damage, your sunburn and so forth, your cancers. But they're small wavelengths. 10 to the negative 8th is the kind of sort of cutoff. And it's not always a clear cut thing here. It's kind of a transition from UV, ultraviolet, into X-rays, which obviously have some benefit for if you low exposure rates for like medical X-rays and for your teeth, for your dentist. As long as you don't get too many of those. There's naturally occurring X-rays all the time, just not that many. You just don't want a lot of concentrated X-rays because it can be harmful. And then the highest energy, most harmful of all, gamma rays. And once again, they are hitting you naturally all the time, either from the Earth or from the Sun or from outer space. But there's just not that many, so it's not in general harmful with the few that are hitting you. So the farthest extreme here is 10 to the negative 13th meters. Once again, all of these things are basically the same nature, the same diagram we would draw at the top of this page. They're just different sizes and different energy levels of each of these particular waves. And only ones that we can sense are the ones that are reacted to by the rods and cones in your eyes can detect these. The rods detect the colors, and the cones in your eyes, in the back of your eye, detect the different colors, and the rods detect the brightness. This doesn't show up too well, but it's just kind of, if you want to take this and expand it, it's the same thing. In the very middle here, this middle thing, I have radio frequencies right here, then the visible spectrum right here. It's a very busy diagram, but it kind of puts out like sizes of things, like the large size wavelengths, like, this is a football stadium or a soccer field or whatever, down to the really small stuff on the other side, showing how the wavelengths get smaller when you get over to gamma rays, like DNA and bacteria molecule size. Here's bacteria right there. It's trying to match up the size of things that you might possibly be familiar with to the wavelengths. Once again, all these things are in your room right now. The visible light, if you have light on, all the colors, red, orange, yellow, green, blue, are in that room right now, hitting things. Okay, I've made the case once before, which is kind of a weird statement, that you really can't see light. It fills the room. You can't see red light. You're detecting it when the light coming out of the light bulbs in your room, it's all colors. The light bulb itself looks white to you, or a yellowish white to you, or maybe a bluish white, because there's different amounts of different intensities of the different colors possibly mixed in, depending on whether it's an incandescent, fluorescent, or an LED. The bottom line is, your eyes detect light. They actually aren't seeing the light. You see the things that the light hits and interacts with. So you see somebody with a red shirt on, you see the red shirt because red light hits that shirt, bounces off that shirt, and goes into your eyes. You're detecting the red light. So we say we see the red light, but really you're seeing the shirt. That's an interesting thought, I think. So once again, it kind of shows you where, in this level down here, where these particular waves come from. Like radio waves come from TV antennas or radio antennas. One of the microwaves, obviously, they use microwaves. Hopefully they're contained in that microwave, which they are, because they can be damaging to you. It turns out that microwaves are lower energy than visible light. One of the reasons why they're useful, though, in cooking food is because the frequencies resonate with water molecules. If you ever try to heat up something that's not doesn't have a lot of moisture in it, and a microwave, doesn't work too well, because microwaves tend to resonate with water molecules and make water molecules absorb energy. And so it'd be dangerous for you, obviously, to be in a microwave. We're too big, and you don't want to put anything living in a microwave. But it messes with water molecules. And that's why it can heat up food. Even though on a per wave basis, microwaves are less energy than just red light. Even though red light is the lowest energy of light, microwaves are even lower energy per wave, per photon. And then the sun here in the middle gives off all the visible light, including also some ultraviolet, infrared, and then other sources of some of the high energy X-rays. They naturally occur by radioactive materials and so forth. And we can create these things in labs. I'll talk about that a little bit here in a minute. Okay, here are two old equations. This is the magnetic induction equation, the magnetic field surrounding a current carrying wire. I forget which unit that was. Either 19 or 20, no, 22, I think. It was unit 22, pretty sure. Magnetic field around a current carrying wire. And then this was in unit, I forget once again, 18 or, doesn't matter. The capacitance equation, the physical characteristics of a capacitor. C is capacitance in farads equals the dielectric times epsilon 0 times the area of a plate. This should be the area of the plate here. This is area of plate. This is the distance between the plate. It's not really that important because I just want to refer to this equation because we see a couple of constants here that are going to show up again. So over here, the important thing is this. We had this, the vacuum permeability of free space. And we talked about this when we did this equation, but I want to focus on that right now. It's a constant in physics in the universe. And this is a constant. These two constants, we want to talk about them more specifically right now. They have a value down here, and we use them. When we did those calculations, we gave you those numbers as numbers you don't have to memorize. But here's the interesting thing, a very, very interesting thing, I think. Right here, I think it's a kind of a wonder of the universal system and how things are designed and how things kind of work out. I don't think this is just random, but some people say it's just random. But C is what we usually call or refer to as the speed of light, right? It's the speed of light. Well, it's really the speed of all electromagnetic waves because all electromagnetic waves are just different sizes of light. Well, they're not light. The specific kind that we can detect we call visible light. But they're all the same thing. They're all the same nature. We draw the same diagrams. They all travel at the same speed in a vacuum. And they all have different energies, as I just went over. But interestingly enough, if you take the square root of 1 over the product of epsilon 0, which is the permittivity of free space, okay, that dealt with electrical systems, okay, like the capacitor. And then you have mu 0, it's the permeability of free space, and here are the numbers for that. You can plug those in this equation, take 1 divided by the product of those two numbers, take the square root, lo and behold, you get the speed of light. That's quite amazing. And they verified this. They've actually measured the speed of light in other independent experiments. There's no reason to doubt that. I'll talk more about that in the next unit. Some of the basic, well, one of the basic famous experiments for determining the speed of light. But if you round that off, it's 2.997. Well, it's 3.0. That's why I have the 3.00 here. To 3 sig figs, that's a proper number of 3 sig figs. All right, so I think it's pretty interesting that if you take those weird constants, in some fashion they seem weird, and you do that and you calculate that relationship, it gives you the exact speed of light. There's an interesting connection there. And there's other people that can probably explain that more in depth, but just for now, I just find it interesting. All right, so generating an electromagnetic wave. How do you generate an electromagnetic wave? Where do they come from? Well, the basic source of electromagnetic waves is accelerating electric charges. And so I'm going to circle that. Accelerating electric charges generate electromagnetic waves. It kind of comes back to magnetic induction, electromagnetic induction. All of those things are involved in this. A moving charge creates a magnetic field. A moving magnet by a wire coil creates an electric field or electric current voltage in the loop. But things have to be moving. Now, here, things not only have to be moving, but the charge has to be accelerating. Not just moving at a constant velocity, but accelerating. I'm going to try to show you a little video here. So, I haven't turned this on yet, but once this turns on, it's going to look like this wave is going to the right. That's the direction of propagation. Now they're using yellow, I believe, for the electric field. It doesn't delineate. So up and down can be the electric field. They have yellow here. And on the out and in axis, whatever axis you want to call that, the y-axis, they have green vectors for, say, the magnetic field. And like over here in this spot right here, that could represent like an electron in it. There's like for a radio station, that would be like a radio tower, a transmission tower, like over here, a metal tower that's vertical. And what happens is the electrons, they create alternating charges or movement of the electrons that move the electron up and down. And as they shake the electron up and down, it's kind of like shaking a rope, but it's an electron. So not because as you move it up and down, you're accelerating. You're speeding it up and slowing it down and stopping, speeding up, slowing down and stopping. So you're continually accelerating the electron up and down, up and down, up and down. As you accelerate that electron, that's changing the electric field. That's the yellow vectors here, from up to down and down to up. And then at the same time, because you're changing the electric field, basically it's kind of putting Faraday's law into play as well. As you change the electric field, you're changing the magnetic field, and vice versa. They kind of are, they are mutually self-generating. We don't need to know the details on that. Once again, I think I'll make the statement at the end of this unit. It's a lot deeper than this, and if you want a further, deeper explanation, you'll have to go to what are called Maxwell's laws. Maxwell's equations, actually, not Maxwell's laws, Maxwell's equations. I'll talk about that at the end a little bit. But let me start up this video, and you'll see the wave going to the right, I hope. So yeah, you should be seeing there that it looks like the wave is going to the right. The energy is going to the right, or along this direction over here to the right, basically. Oh, now they changed the type of animation. They're kind of showing you E and B. All right, so at the end, just to recap on that animation, E is electric field and B is the perpendicular magnetic field. So that's a common way to generate electromagnetic waves. And once again, that's just a small portion. That animation just shows you one direction. The waves actually come out in all directions from that antenna, and they fill all of space. And they would fill the room you're in if they come to the area you're in. So you could receive and then have a receiving antenna that will take that. And what happens in your receiving antenna is it resonates if you turn your tuner to a certain frequency using basically capacitors and inductors. You don't need to know all that. But it will resonate then. It's another example of resonance that we studied in Unit 17, I believe, where the electrons in the receiving antenna can be set into resonance with the sending signal, That was controlled by the sending tower, the transmitting tower. Anyway, here's another interesting relationship between electric and magnetic fields of electromagnetic radiation, or, well, sometimes it's called electromagnetic radiation, electromagnetic waves. And that is C equals E over B. Interesting relationship, where C still is the 3 times 10 to the 8th meters per second. It's equal to the magnetic field strength vector divided by the magnetic field strength. We'll do a problem on that. Simple relationship. That always comes out to be C, 3 times 10 to the 8th. What this implies also is that, right here, the note, that B tends to be weak relative to E. That's why C comes out to be a big number. B is small. Even though you really can't compare E to B. You can divide them. You could never add them because it's like apples and oranges, but you can divide them. But in general, B is kind of small compared to E. This is just a review. This goes way back to Unit 16. The velocity of a wave equals the wavelength times the frequency. So here are some examples to put these into practice. Calculate the wavelengths of the following. So you have an AM radio station and an FM radio station. These aren't actual stations, but AM, I don't know, AM goes like from 500 kilohertz to 1600 kilohertz. FM goes from like, I don't know, 80-ish megahertz up to 108 megahertz. And by the way, AM stations, and these waves, like I said, they're in the room you're in right now. AM means amplitude modulation. What they do is they encode the voices or the music by manipulating the amplitude of the waves. Once again, you can't see any of this, but the radio deciphers this. That's what AM stands for, amplitude modulation. They encode the signal in that frequency by manipulating the amplitude of the wave they're sending to your radio. And FM is frequency modulated. They have what's called a carrier wave. You don't need to know that, but they manipulate the frequency of the carrier wave to encode the music. But they're in the megahertz range. So, for example here. But in both cases, the velocity is 3.00 times 10 to the 8th meters per second. That's the speed of light. C. I could have called that C. But I'm just plugging into V equals lambda F. So for the AM radio waves, I have 3.0 times 10 to the 8th, 3.00 times 10 to the 8th. We're looking for the wavelength. The frequency is 1600 kilo. So it's actually 16, there's the 1600, but then kilo is 3 more zeros, so it's 1,600,000. So if you do the easy division there, you get 190 meters. All right, so they're in the range of like 200 to like 400 meters. Those are the shortest waves. The ones near that end of the dial are shortest waves. So there's ones that are 300 or 400 meters. They're going through that room you're in right now. And their frequency, like if you have, what is it, 890 WLS? WGN is what, 720? WGN is 720. It's 720 kilohertz, 720 vibrations per second in the very room you're sitting in. And that wavelength comes out to be probably around 300 meters. 720 vibrations per second, filling the room you're in, invisible to your eyes. It's amazing if you think about what's going on in that room you're sitting in addition to the magnetic field, the electric field, and the light filling the room. B. What's going on here? V equals lambda F. My pen wasn't working for a second. So 3.0 times 10 to the 8th equals, we're looking for a wavelength. These are going to have even shorter wavelengths because these have megahertz. It's 108, not 1.8. 108 times 10 to the 6th. I'm not going to write that all out. Hertz. You could add 6 more zeros if you want. But you take 3.0 times 10 to the 8th divided by the 108 times 10 to the 6th, you get 2.8 meters. So they have much shorter wavelengths. That's meters. But they're filling the room you're in, because I can tune into FM radio stations. All right. How about this? How long does it take for light to travel from the sun to the earth, given that the sun is that far away? This is kind of just a review question as well. And that is, well, basically it's actually V equals D over T. That's a basic velocity equation. It's not even a wavelength equation. But it's light from the sun. And the key is that it travels at, well, let me solve that for time. The time, then, if I'm looking for the time. The time is going to, if I move it around, is d over v. So the time, that's just a reformulation of that equation by moving things around. The distance is 1.50 times 10 to the 11th meters. That's like a 94 million miles-ish. Okay, but we want it in meters. Divided by the velocity. Well, the velocity is 3.00 times 10 to the 8th. Where did I get that from? Once again, you have to know that it's light. Any kind of electromagnetic wave, like in the previous problem, radio waves, still the same speed in a vacuum because most of the space between the sun and the earth is a vacuum. The only time light slows down is when it goes through glass or plastic or water. It can go through water, but it's not traveling through any of those things when it gets to your eyes. A little, maybe in the room you're sitting in, it might have to come through a window, but that's very minimal. So if you do the math there, that comes out to be, the time comes out to be about 500 seconds, which, okay, that's okay, that'd be your answer. But if you divide by 60, that comes out to be about like 8.3 minutes. That makes a little bit more sense to me. 500 seconds, okay, you could circle the 500 seconds. 8.3 minutes, that's about how long it takes light from the sun to get to the earth. And it's all the colors, and it includes infrared and ultraviolet and some gamma rays as well and so forth. But most of the light given off by the sun is visible light. Once again, it's a kind of a cool thing, very important thing to us because it's what sustains life on Earth is the light from the sun. It's an energy source. Okay, number 3. All right, you have a 60 hertz AC power radiating radiating electromagnetic wave having a maximum electric field strength. Okay. Okay. So what's the magnetic field strength? What is the maximum magnetic field strength? Well, once again, that equation, if you look back to the top there, is C equals E over B, top of this page. We're trying to find the maximum magnetic field strength. So I don't really care about the frequency here. I could use that to find wavelengths and things like that, but I don't need that. I need to calculate B. So I'm going to reformulate this equation. So if I manipulate that equation, it's going to be B equals E over C. That's just moving things around. Move the B to the left, move the C to the right. So B, which is what I'm looking for, the maximum is going to match up to the maximum E field. It's 14 kilovolts per meter. That's 14 and then 3 zeros. Okay, so it's 14 times 10 to the third. Divided by 3.00 times 10 to the 8th. That's the speed of light. So I do the math there. The magnetic field strength around this wire, high power, this power line, is 4.7 times 10 to the negative 5th Teslas. 4.7 times 10 to the negative 5th Teslas, which is about the same as the strength of the Earth's magnetic field in the room you're sitting. One of the implications here are some people are scared about high power lines near their houses, and this is basically telling you that you have to be really, really close to even get this. That would be the maximum magnetic field strength given these conditions. If that's what the electric field strength is in this particular wire, 14 kilovolts per meter, they're not harmful if you look at that number. So that's just something to think about when they talk about high power lines having a negative health impact. There's more you get to consider there, but based on this, the magnetic field, the maximum magnetic field strength generated right now is no more than the Earth's magnetic field. Maybe the electric field has detrimental effects, but the magnetic field is the same as the Earth's magnetic field. So as I've said before, though, for a more comprehensive approach to these topics, we're not going to get into the deep, deep math. And this is pretty much the first half of chapter 24. We're not going to get into the real deep, complicated math with Maxwell's equations. So we're going to stick with some pretty easy stuff here in this particular unit to finish off magnetism and electromagnetism. And next up will be optics. So stay tuned.